Going to work through problem 4.20 from chapter 4 of Taylor's Classical Mechanics. This is a problem on taking the curl of a force, and that is a force vector that we're going to take the curl of. So the curl is this del or nabla operator crossed with your force vector. And we know that this operator looks something like this. So for part A, we're given the force Kr, which is Ki plus J plus K, Xi, Yj, and Zk actually. Let me rewrite that. Xi plus Yj plus Zk. And this K here is just a constant. So in this case, our gradient operator, the gradient is when we dot it. In this case, we're taking the curl, so we're crossing it. And when we do the cross product, we take the determinant of this matrix. And we can pull this K out to the front of this. So when we take this determinant, we have I times, that's going to be the partial with respect to Y of Z, is just going to be 0, minus the partial with respect to Z of Y, which is also 0, minus our J, and that's going to be partial with respect to X, 0, partial with respect to Z of X, also 0, plus our K. That's going to turn out to be 0, minus 0 once again. And it turns out that our curl is 0 for part A. This means that our force is conservative, and the vector field of this force is irrotational. That's also what that means. The curl is telling you the rotation at any point in the vector field. And this is an irrotational vector field because it's 0 at all points. And yeah, that also means that it's conservative when the curl is 0. So for part B, we're going to be given a different force. Our force is ax by squared cz cubed. Plus by squared plus cz cubed. So don't forget it. There we go. So we're going to do the same thing again. With our del operator here. This time we're acting on ax by squared and cz cubed. So when we take this determinant, we're going to have I, that with respect to y is 0, this with respect to z is 0, and we're going to flip the sign, have our j, that's going to come out to be 0, that's also going to be 0, plus our k, and that's going to be 0 and 0 again. So once again, our curl, the curl of F, our force vector field, is the 0 vector. And it's the same as being 0 It's the 0 vector. So this is also conservative. Conservative, irrotational. And I'm going to add that up here too. Conservative and irrotational. So let's look at part C. Our forces AY squared, BX, and CZ. And it was, just CZ. So that's our force. Now let's take the curl of that force. It's going to be the determinant. Hopefully you're seeing the pattern now. To take the curl, you're going to set everything up the same here. You can memorize what the curl would be with respect to each component. I think it's easiest if you know how to take the determinant to set it up like this. Less room for error that way. So now, let's see what we get. We have I, that's going to be times derivative of this with respect to y is 0. Derivative of this with respect to z is 0. Flip the sign, we have that j. That with respect to x, 0. This with respect to z, 0. Plus k. This with respect to x. Finally, we're getting something that's not 0. We're just going to have that constant b. As stated in the problem, b was a constant. This with respect to y is going to be minus 2ay. So we're subtracting 2ay. So that means that our curl, in this case, is b minus 2ay in the z direction on that k unit vector. This is not equal to 0, so this is a non-conservative force. And this field does have rotation. It's not an irrotational vector field, so it's a non-conservative force because the curl of that force is not 0. Pretty sure that's all the question asked us. And yeah, if you hadn't seen curl before, you're just taking your nabla or del operator, which is del over del x, del over del y, and the z component of that, and taking the cross product of that with your force.